All right, folks, a very warm welcome to Support Vectors Meetup. The Support Vectors Meetup group is sponsored by a company that is a training AI training company, Support Vectors AI Lab. We provide, if you would indulge me for a moment of advertising here, we provide in-depth hands-on training in AI, which is very different from the typical video-based online training that you go through. Here, a lot of teaching assistants and a complete staff work with you very closely. We give you access to really amazing computational hardware, especially when you do the boot camps. You get you do have access to full access, root level access to GPUs or a Linux servers with GPUs. And it's a pretty vibrant learning community where people not only learn from the instructors, they also learn from each other. And we have been very proud to say that many, many startups have come from, from our training. So, with that, one of the traditions we do is as a weekly outreach, we do a weekly paper reading. In this, we encourage you to propose what should be the weekly, which paper we should read next week and the week after that. And generally, if a paper is proposed, we almost always cover it. The only question is when. So, with that bit of preface, let us launch into the paper of today. The paper that we are going to cover today is called ColPali. It is part of the, if you look at the way we organize the meetup, we marked it as a series of three paper readings, and they were the Colbert paper. I'll write it down. A paper called Colbert. Oh, sorry, that's too fat. Um, Something called Colbert and something called Pali, Pali star, like Pali 1, 2, 3. Let me just say Pali 3 and Pali Gemma. And today, in this progression, is the final paper called Pali. Now, for those of you who have been attending the previous two sessions, today will look like putting the pieces together uh, and solving a very complex problem that has been sort of plaguing the world of RAG for quite some time. So let me first speak to the problem, and then as we move along, I will give a very brief retrospective of what we covered in the previous two sessions. So today's session is called PAL. Before we go into that, I think it is sufficient to say that it is worth actually going through a very, very small introduction to RAG, retrieval. Retrieval augmented generation. What does this mean? It means this, and I'll just keep it brief. Suppose you have an LLM. Imagine that you're sitting in front of one of these LLMs, whether it is your Mistral or Llama or one of the commercial LLMs. Let's say that you're sitting in front of uh, Cloud Sonnet or Gemini or OpenAI, ChatGPT. What you typically do is you send in a prompt. Now, the word prompt has many synonyms. It is often also called in the Googlish language, you often see it being called the prefix is sent in or input. These are all synonyms, input to the LLM. And what comes out has itself many names. You can, of course, counterpart of input would be output. More formally, you can call it continuation. Continuation. It is also called suffix, especially in the DeepMind papers. Now, this LLM has been trained with great effort. Typically, it takes a few months and tens of thousands of GPU to train a particular LLM. Like, for example, um, Meta revealed that to train Llama 3.1b, it took them, so Llama 3.1 full size model, which is hundreds of billions of parameter. One of you can remind me, it's 400 billion or something like that. Parameter model, full size, it took 24,000 GPUs. GPUs. We are talking of things like H100, which are the state of the art, or H100, H200, the state of the art GPUs. And it took months to train. And so it is not feasible to for these LLMs to stay absolutely current and up to date. Oh, thank you, Jorge, for pointing out that this is 3.5. It is 405 billion parameters. And when you train this, it is obviously the practical feasibility is you can't be training every single day on the latest data. So whatever data exists, you pick a certain time, you take data from the world data, let's call it, world data, which contains news, which contains other facts, discoveries, research papers, etc. All of it at that a point in time is captured. It becomes the training data, so many million or trillion tokens. Like, for example, this was trained on trillions of tokens, trillions of words, think of it roughly like that, to produce a trained model. So when now the one limit, there are two limitations that come out with the LLM and getting answers straight from the LLM. And it becomes quite evident when people try to use an LLM as a de facto search engine as it has emerged. You ask it a question. For example, if you ask it, who won, who is the latest presidential candidate from for the upcoming US election from the two leading parties? If this model was trained a couple of months ago, it would, as you know, come up with a different answer than what is currently true, because there has been a surprise change of one of the candidates, or substitution of one of the candidates in the United, if you're keeping track with the US politics. So it is, in other words, not up to date. Let's write down the limitations. Not up to date, date in information. That is one point, number one. There is another point. These models can only be trained on data that is publicly available or that these companies have access to. So, for example, if it is Meta, one would imagine that it has scraped through all its Facebook and other data. If it is Google, it has, oh, again, Shirang, thank you for pointing out, it is 15 trillion tokens. So 15 trillion tokens. And it was trained on 39.3 million GPU hours. So just shows how expensive it is to train those models. Anyway, nevertheless, you have certain limitations. These are the limitations. The limitations are they are not up to date with information, and they still see information that shows up in the public web or that is proprietary to the company that's training the models. Google has its own Google data, perhaps from searches. Uh, Meta has its own data, maybe from the social medias that they control. And then there is obviously the public data. But one crucial thing that it doesn't have is your confidential or proprietary data slash proprietary data. So imagine that you're an enterprise. Then the last thing you want to do, suppose you're Boeing, then the last thing you want to do is let a LLM be trained on all your secret sauce on the wingspan design and the engine design and so on and so forth. Right? Every company would like to hold on to its confidential uh, information. There are a lot of things that are confidential within a company. Nevertheless, you do see that the LLMs are powerful, and if only you could query into that data also. So for this, there came a way to augment the LLM. So it is called LLM generates a response. So this process is called generation, and therefore the word generative AI. So what you do is you augment the generation with a search engine. What you could do is you use the standard search engine technology. This search engine technology is often called information retrieval. The formal word is information retrieval. The IR, abbreviated to the subject of IR, information retrieval. What you do is you take all your internal documents, you go through a process of indexing into a search index. You maintain a search index. And then when user gives a query, let's say a query comes in, let me give it another color. User query, Q comes by. What you do is you send the query first to the search index. And you search the search engine. It will produce search results. Now remember, the search index is on, let's say, your private data, or it may be more recent news, etc. Then as you search for this, and sometimes there are all these sort of paid information sources, like a lot of textbooks. Of course, you can't just the open LLMs can't just index them because they have copyright notices, etc. Now, if you do have a copyright, if you are paid for that content, then that also goes into your search index. Now you get the search result, and then what you do is you create a expanded prompt. What you do is you create a prompt which contains, using the search results, now answer the user query Q. So when you send this information to the LLM, what are you doing? LLM is a generator. Remember, this is it's a generator, right? Generator or generation of response. Or answer. But this generation, which the LLM does, has been augmented with this extra information. You're not just sending in the query, but you are sending in the search results. Search, more formal word is retrieval. So what you have, this whole process is called information retrieval, as we mentioned. So you say this is retrieval augmented generation. So this is RAG. And by now, almost everybody is familiar with RAG, but I thought I would just throw in a very quick primer about what it really is. Now, so with this RAG as a background, this paper becomes important. So what are the real problems that you face in RAG? It has to do with the search indexing. There are many issues with search indexing. First is that you can do Uh, you can do traditional search. You can do traditional search as in, basically keyword based. Think of your Elasticsearch and so on and so forth. Solar, Elasticsearch, and all of that. What do you have? You have keyword, and you have list of documents that contain that keyword. I won't cover that territory again because you're familiar with that. And so when you come across a term in the query, you just pick up all the documents that you have already made a note of in a table, index table, and that's why it's called index. And a very intuitive example of an index is just take any textbook and look at the end of it. You will see an index. For every term, you will see the pages on which that term occurs. And that is a good way of thinking about index. Right. So you can look into a traditional index. More recently, there has been the concept of semantic search. Semantic search does this. Given a document, DI, you convert it into a semantically, you create something called a semantic embedding. Semantic embedding, EI, such that two documents, if EI and EJ are close to each other and EK is far off, then it is because these two documents, these two documents, uh, these two, if you go back and do an inverse mapping, let me call this mapping F, right? If you go back, this is the embedding transformer, but if you go back, you will find that DI, DJ are talking about similar things, but DK is very different. Right. So this kind of a embedding is called semantic embedding, and these are called vectors, semantic vectors. And one of the achievements, and this was first in the sentence BERT paper. The power of this is what you could do is you could take all the documents in your corpus, documents D1 all the way to DN, and convert all of them instead into a collection of vectors En in a semantic vector space. And these things you could put into a ANN, approximate nearest neighbor index, which do extremely or highly efficient k nearest neighbor searches. Right? So it can tell you if you take a query so what you do is you take the query text, I can convert it into the query vector query and then find its k nearest neighbors. So for example, it may be E11, E19, E35, let's say, just randomly, the three nearest neighbor. So from that, I can conclude the document, 11th document, the 19th document, and 35th document, they are the search results. So this is the world of semantic search. Now, this world works very well for text. Very well. Now comes the problem. In real life, you encounter documents, like if you look at any PDF, especially, or a web page, what do you find? Complex documents. They contain not or HTML. What do they contain? Are they just walls of words? They're not walls of words. They're not, for example, they are not a literary novel in which everything is text. Typical documents, especially corporate document, they will have tables. A doc will contain tables, spreadsheets. spreadsheet, let's say. They will contain images, right? They will contain images. They will contain charts. So, for example, some kind of a chart, and then they will contain text. So, in other words, even though documents are written in languages, the languages are rich and varied. They are multimodal. A lot of facts are presented in spreadsheets. Some are depicted using an image. Some are depicted using charts. And then there's text. So as people have built these RAG pipelines, and here at Support Vectors, we have been teaching RAG now for more than a year. One of the most common things that people face, we take them through a phased exercise. The baseline RAG is we give them documents that just contain text. And so if it is just text doc, converting into embedding vectors is easy, right? If on the other hand, we give them images, only images, then as a pure search engine, we can do, like, for example, you can use clip and siglip, etc., which is just a better clip with a sigmoid loss function kind of things, also into embeddings. And you can get away with it. But how in the world do you deal with a document that contains, on a single page, let's say a page will contain a page with all four. Suppose you have this and text. Lots of text. Suppose you have a page that contains everything. So this is where the complexity of things comes in. Experiences, what people do is they will go to the MTEB leaderboard. It's a particular benchmarking thing, and see, oh, which is the best sentence encoder, which is the best, what is the best way to encode a document. And maybe these days BGE is supposed to be very, very effective. You may pick that. Problem is, it works well with text. What about the rest of the modalities? You have spreadsheet, you have chart, you have images. So there has been an effort to make sense out of it. So other than just RAG, people have been asking, can a large language model understand a spreadsheet? So for that, there is actually a research paper called Spreadsheet LLM. If you want to understand charts and you can look up this research paper, there's literally a bunch of a pretty good research that has been done. And one paper that is in this space is called the chart LLM, for charts. So do you notice that you're solving the problem piecemeal? And if you come to images, of course, you can use the visual encoders like clip, etc., with contrastive loss. And if you remember in the last session, we talked about the sigmoid one, siglip, which is basically clip with a sigmoid loss, amongst other things, but that's a core idea. It leads to better results. Instead of a softmax, you use sigmoid. But they are both contrastive loss mechanisms. But you realize that this is all very piecemeal, right? For everything, for every modality, you use something else, right? Charts, you use something else. And let's say for images, you use something else. And then obviously for text, Let's say that you are using a sentence encoder, for example, BGE or something like that. So do you see the fragmentation in the landscape? You have four modalities and you do need four different kinds of things to deal with it. So what really happens, and this is a frustration you hear, and that's actually one of the things we used to teach people, is RAG is not as simple as you think. What you have to do is when you deal with complex documents, you have to, oh, by the way, there is not to mention the fact that how do you know in a page what all things are sitting there? So for that, there is a layout LLM determines the layout of the page. So by now, I hope the message is clear. And this is, by the way, very, very practical reality that we face here, that if you deal with real life and you create realistic pipelines over complex documents, your pipeline is quite complex. You need a layout to figure out what is there in the page. Then you need a spreadsheet technology to extract the data or understand the spreadsheet, the tables. Then you need chart LLM and this to get some sense of the charts. To understand image and encode them, you need something like clip, etc. And for text, of course, the easy part, you have a sentence encoder. And then you end up with a vector database. Even when you get a vector database, now the next thing is to search into it. When you search into it, the naive way, which is the way 99.9% of the RAG implementations that I've seen, I would go so far as to say almost 100%, but not quite, that you see is one document or one piece of chunk, one chunk of text. So these in other words, a doc becomes chunks. Chunks are these pieces of text, image, charts, spreadsheets, etc. Chunks become vectors. Now, what you do is one chunk, there's a one-to-one mapping between a chunk, and by chunk I may mean any of these things, 1:1, to a vector, a particular vector embedding. Right? Chunk I becomes a vector I. And you put it into a vector database like FAS or Qgrant, or whatever, which all sit upon FAS and its variants. And you search for it. It gives you back the results. It turns out that that itself is not the best way of doing it. There has been a work that we covered 2 weeks ago in a landmark paper called, let's use another, we call the Colbert paper. Colbert. It uses something called late interactions. And I'll review the concept in a little bit. But first, let's go through this paper and see what this paper is trying to say. So I'll start on this paper now from its abstract. I think we have enough background now to start making progress with the paper. It says, documents are visually rich structures that convey information through text as well as tables and figures, page layouts, or fonts. And this is important. Change of font, making it bold, right, italics, etc., conveys things. If you read a scientific paper, you'll notice that the mathematical equations are rendered in a different font. While modern documents or document retrieval systems exhibit strong performance on query to text matching, they struggle to exploit visual cues efficiently, hindering their performance on practical document retrieval applications such as retrieval augmented generation. So it's saying what we have been saying. If you take a document, if all you do is extract text from it, then you do have problems of efficiency and problems of performance. So what do? If you encounter a table or you encounter a chart or a picture, in a baseline implementation, you may just ignore it. Many of you use PyPDF or whatever it is, Tika, Apache Tika, etc., to read the text out of a PDF. And if you notice, or HTML, and if you notice carefully, what it does is it basically either ignores the tables and the images or absolutely massacres it. It will just take out some text that it might spot. The alternative that people do is OCR, optical character recognition. Sometimes they will treat the whole page as an image. They'll go through OCR, they'll do a layout detection, they'll do very, very complicated processes to try and convert just about every piece into text. When you try to do that, it becomes a really complex pipeline. And this is real life experience, guys. I've seen and I've guided people to create production pipelines for RAG. And it is the real life is very different from the lovely pictures that you find on tutorials. It's a complex beast. So that's what they're alluding to. To benchmark current systems on visually rich document retrieval, we introduced the Visual Document Retrieval Benchmark, VIDORE, composed of various page-level retrieval tasks spanning multiple domains, languages, and settings. So this is the first contribution. Contribution number one, let me highlight the contribution. To benchmark, so one contribution is they're creating a benchmark. They're saying that, hey, there are no good benchmarks which look at visually rich documents, which is, think of HTML pages, PDFs, and so on and so forth, textbook PDFs. So they are creating such a benchmark and they're creating such a data set, which is one big contribution. And then they go on to say that the inherent, and then comes the second contribution, the inherent shortcoming of modern systems motivate the introduction of a new retrieval architecture called ColPali, which leverages the document understanding capabilities of recent vision language models to produce high quality contextualized embeddings solely from image of documents. So the word ColPali itself is composed of, if you have been talking, as you can see, it is sort of a portmanteau made out of Colbert and actually ideas of Polygemma, or you can say Pali. And these things add up to this plus this is equal to ColPali. That's the message. And that's a clue. That's where they're heading towards, but they haven't mentioned that in the abstract, but you'll see they'll go to it. So what they're saying is that what if we treated a document not as little areas made out of text and charts and figures and tables, but what if we treated it as a visual language understanding problem? Now, visual language models, for example, the VITs, the clip and the siglip, clip, right? So, for example, you can give it a picture of a scene, and you say, "What is it?" Give it a caption, and it would produce a caption for you, or it can do question answering for you. Lava, blip. There are many of these. They can all help you get some answers about questions, about visual images. So what they are saying is, let's take a different idea. We have tried the old approach of the RAG pipeline. What if we did RAG, but we did we did RAG in a completely different way? What we do is, we just treat each page of the PDF, they don't say it here, but you'll see in a little bit, they say, let's treat each page of the PDF as an image and just as an image. So imagine that each page, like for example, in some photography book, you often see that most of the pages are just landscape pictures or portraits or things like that, scenes or whatever it is, figures or photos. So imagine that you could treat every page as just an image. Can you use that to create RAG? Or can you do that to search through the document? Can you give it a query and can you do search into the document or into the PDF, simply using each page or treating each page as an image. So let us parse it out. Let's unpack it. How would we do that? Right? You could do that by saying, "Oh, well, that is easy. I don't know whether it would work or not." You could take a visual language model. Suppose you have a document and just a VI. Think of just clip. You take an image and you break it up into. Here I did. Let's say sub images. You don't take, or maybe let's not so many pages. Let's just make it 4 pages. So here is one figure, figure 1, figure 2, figure 3, figure 4. You treat it as 4 images, right? And you basically say, this document I can do if I pass it through, let's say clip, or in this particular case, siglip, right? It will become a bunch of visual tokens, right? It will become a bunch of visual tokens, right? That is what visual language models do. Convert text into tokens. They create embeddings. You pass it through the transformer, and you will end up with vectors, contextualized vectors. Now, you may have done it separately for each region, like this one, then this one, and then this one. And you just put it here, those vectors, 4 vectors. And let me just put it this way. You could do it here.
So Asif, is 1, 2, 3, 4 the pages in the document, or?
No. Those are 4 parts of the same page.
Of the same
One
page.
page.
Okay. Yes.
So you break it up into parts. Now what happens is, suppose you were to give it a query and you look for results. We know that just a visual language model, this is called a visual language model, a pure visual language model like CLIP. You're more familiar with CLIP. Many of you may not know about SIGLIP, but SIGLIP is just a better version of CLIP. Think of it this way. It performs better. So these are called visual language models. If you ask it a question, then the performances are reasonably good. But where they are not so good is that these pieces, they are not aware of each other's context. They are not contextualized. Are we together? So they are not contextualized. So the contextualization is a topic we covered, if you remember. That was the core idea in the Pali paper. Oh, sorry. In the Pali. We did that, Pali and Pali Gem. What you do is you take this, and this picture here, the research paper shows it here. What you do, look at the lower figure. I'll expand it out a little bit. So you note, I deliberately broke it up into only 4 parts because that's what this paper diagram is doing. Now observe this. What do? You pass it through a vision encoder. What will the vision encoder come out with? For each of these parts, it will come out with a vector. So for example, this is A, B, C, D. So it has come out with A, B, C, D vector. Now, those vectors are very high dimension, and you might choose to project it down. You need to adapt it to a dimension that an LLM needs. Now, if you have been through the Pali paper, you know this, but I'll just explain it to you. The last time. Why an LLM? Why would you pass it through an encoder decoder or just a decoder? Once again, because think of it as just a very powerful attention layer. You need an attention layer because of this cross interaction. See, A needs to pay attention to every other one. And likewise, every one of them, they need to pay attention to each other's tokens, isn't it? Each other vector. Each of these vectors gains some meaning from what they are and also gains meaning from what is there in the rest of the page. And that kind of attention, the easiest way, obviously, the way we do that is through attention. And in a more sophisticated way, you pass it through either an encoder decoder or a decoder only. Right? These days, you just pass it through a decoder-only LLM. So what we'll do, what's the difference between, for example, this vector and, let me take this, between this vector coming out, this vector versus this vector, this vector. What's the difference? Sorry, this is too fat. This vector. What is the difference between the green and the orange vector? What happens is that they have been contextualized. These have been, exactly, these have been contextualized. Let me write it. Contextualized. In other words, each vector, as they pass through the LLM, they do a lot of cross attention and understanding. Oh, is this what you are? Okay, I am this, and so on and so forth, right? To put it in a very intuitive way. And so, once again, as it comes out, what they do is, for reasons of computational efficiency. So, by the way, why do you have a projection layer here? You need a projection layer here simply because the LLM may be expecting vectors of a certain dimension. The vision encoder may be producing vectors of a different dimension. So you just need a simple projection layer to align it to the LLM. Now, this particular projection layer, though, is different. This projection layer deliberately reduces the dimensionality because the LLMs produce vectors, again, of very high dimension, like 1,000 dimension or something. They reduce it down to 128 dimension. So what happens is a page goes in and it becomes vectors of 128 dimension. Are we together, guys? Does it make sense? You project it down to a lower dimension. Now, you project it down to a lower dimension because we want to store these vectors into our vector database. So both for retrieval, for storage in terms of how much space you use, how much, and especially when you load it into memory, how much memory footprint there would be, right? And just for compute efficiency, it is a good idea to reduce the dimensionality of this vectors. And what they found is that reducing it to 128, you don't lose much. It does quite well. Now comes the interesting thing. You notice that one document has become all of these vectors. Now comes the actual inference time. So what you do is you take each page and you store it as all of these vectors, a collection of vectors. Then comes the second part of the journey. Suppose, so this is the offline part, means you do a batch processing job. The moment documents come, you shred them down to pages into these vectors, store it into the vector database. Now let's go to the inference time, what they call online part of it. At the online time, the user will ask a question, isn't it? For example, the user has asked the question, what are VITs, right? Well, VITs, since they're involved here, let me use another word. What are cats? Or what are panthers? So then what will happen is, for that, we do the same thing. You realize that you can take the query, you can pass it through a LLM or an encoder, you can you do a projection, and for each of these words, you can come up with vectors, isn't it? A d-dimensional vector, d being the same as this dimensionality. You can come up with a vector for each of the tokens. Now observe something interesting. We are not converting the entire query into one vector. Like the traditional RAG and the way vector embedding works, as I mentioned, traditionally, one document becomes one vector. Remember, this is the message. This is the more traditional way of doing it. One document becomes one vector. And now I'll just whet your recollection about a new paper, the Colbert paper. What Colbert paper said, and just a quick recap, the message of the Colbert paper was that when you convert a document or a chunk of text into, take a text and make it into only one vector, you lose its semantic richness. And so when you do similarity, k-nearest neighbor searches, your results are not so good. The Colbert paper asserts correctly that given a text I, you make I1, I2, I3 for every token. I mean, make it lots of a bundle of vectors, IK, uh, right? K vectors. So you go and create all of these vectors. And for this text, store these vectors in the DB, in vector DB. Then when queries come, let's say that a query has come, what you do is query will again be like, what are, let me take the word, what are panthers? And so once again, you break it up into query one, query two, these vectors, query K vectors, right? And then what you do is, or query, let me just call it, then they don't have to be the same number. Let me just say query n vectors. You do it n vectors. Now for what happens is maxim, this was the main formula from the Colbert paper. If you remember, it is now, the name has been changed from maxim to late interaction equation, because that's the name that has stuck these days. So what this is saying is something quite simple. I'll explain this thing to you. What it is saying is, take Q1, this vector, and find the biggest dot product that you can have with one of these. So figure out which of these has the biggest dot product. So let us say that it has a biggest dot product with EI 7. Take this. So this is the biggest of the dot product. Then you add Q2, and then so this is the max, right? This is the max of them. Find, maybe this has a I of the document, this has the max with the third vector in your document. So like this, and for every document, you find the similarity score like this and use that similarity score for KNN. So that idea is the Colbert idea. And they show fairly convincingly that using late interaction searches are far more effective than um, single vector embeddings. Now, single vector comparisons. Now, obviously, that raises the question, isn't this rather expensive? And so what people sometimes do to keep the cost down is that they will use single vector comparisons to get a candidate list, a huge candidate list, and then they will do the late interaction. So they'll maintain two databases, a fast lookup to get the candidates, and then a late interaction for cross, as a sort of a cross encoder to re-rank it as a re-ranker, to do a better re-ranking of those query against those documents. Right? So then you're not comparing it against a billion documents, you're comparing it against a candidate of, let's say, 100 documents, when you have to pick, let's say, 5 out of them. So there are ways to make it fairly efficient. They do that. So that brings us to the last stage of this picture, the diagram that they're trying to mention. And I'll now go back to this diagram and bring it. So what happens here? This text goes in, the query goes in. As you know, as it goes through the LLM, it will become these vectors. They'll go, you project it again down to a lower dimension, project it down to 128 dim. And then you do this maxim. So notice that here they call it maxim, but it is the same equation. And I suppose they use slightly different language without realizing it. Here, they're using maxim because that's the original word they used to use in the Colbert paper. But here, they have mentioned it as a late interaction equation. It's the same thing, right? And then a little bit about the fact that the rest of the things remain the same. It talks about contrastive loss, which was used to train the embeddings, just like you would train clip for other things, or you would train any, not clip, sorry, any kind of a sentence embedding thing using, take a dog, take a similar dog, take a random dog, and use the triplet loss to do that. They still do that. It goes to the paper of Khattab and Zahari, which is so this Khattab and Zahari paper has become very famous actually. We covered it. People often refer to it as the Colbert paper. And both of these guys are at Stanford. So that is that. And if you get that idea, you pretty much understand what the paper is saying. It's saying, see, we are going to do something quite interesting. We are going to use the power of Colbert to do similarity search, and we are not going to do all this text extraction, table extraction, image, this and that. We are not even going to convert and extract text at all. We are going to use the visual language model, visual encoder, to just treat every page as an image and basically go divide the page up into a grid, into smaller parts. And then basically each page will lead to its contextualized vector. So these are contextualized vectors. This and these are also obviously, if you pass text embeddings into word embeddings into um, LLM, you'll end up with contextualized vectors on both sides. So you're comparing contextualized vectors of the document with the contextualized vectors of the query, and you're using the Colbert late interaction or the maxim formula to do that. And when they do that, you would say, all right, my goodness, are you saying this is actually going to work? Because in reality, what was the traditional retrieval, the RAG pipeline? Imagine a page like this. So this is the old one, the old way. Or let me just call it not the old way, they call it the standard retrieval, because this is how 99.9% of the implementations all work. What you do is you take this page, it has figures. You first you can use OCR. You can, if you do OCR, you will detect all of these boxes. Bounding, if you remember optical character recognition, just puts bounding boxes, text, something, something, right? Then you pass it through a layout detection engine, layout LLM. It will say, oh, this is a text, this is a heading, this is a image, this is a heading, text, so on and so forth. Each of those elements that it finds, a layout detection finds, becomes its own chunk, and it goes through its text embedding. When it goes to the text embedding, some things are also lost in the process. For example, what do you do with the image? Traditionally, most companies that I've seen, they just hope that missing the image won't do much harm. Some companies which are more sort of careful because the image has a lot of data, try to pass it through something, something else, like detect whether it's a image or it's a chart, then use some data extraction or understanding of that image, something or the other, very complex. So these pipelines are very complex, right? It is not as simple as it looks in real life. And so what they're saying is don't do any of that. Just in one shot. So you realize that this is a very simple process. Treat the page as an image and then just go get your image, contextualize image vectors. That's all. And compare it to text. So this is a classic example of, in some sense, a multimodal learning or visual language model used along with Colbert with great efficiency. And thus, that is what the paper is about. There's a technology. Does it actually work? They show actually, so they created their own benchmarks. I will skip the benchmark part. They've made a very good benchmark, but I'll focus on the actual the part, and the results really speak for themselves. So let's look at this chart a little bit carefully. Uh, when we look at this chart, first let us think of the old way of doing things, which is just statistical analysis. Right? When you see BM25, this is your statistical analysis approach. I'll just put it in yellow, right? Unstructured, plus some captioning. This is there. So look at these numbers. So progressively, as you go down this list, see how things improve. First of all, observe something remarkable. A plain vector embedding of the text does better than just using a contrastive VLM like CLIP or SIGLIP. You can't just use a visual language model to treat it purely as an image and get away with it. It doesn't work. It's actually, the numbers are much worse. Look at this. These numbers are much worse than what's highlighted in yellow. Then comes the way uh, these guys have started doing. They use Siglib, their better version. Then they bring in Pali, which we covered last time. And then they finally come to ColPali. And I suppose the point they want you to notice is as they bring one idea after the other into the game, progressively there is improvement. And actually, if you look at it, in just about all the benchmarks, ColPali beats the state of the art. And that is why recently it's been getting a lot of attention. Because there are two things. Your rack pipeline now becomes much simpler, much, much simpler. But at the same time, your results get better. So, obviously, when you have results like that, it represents a milestone that everybody pays attention to. And that is the value of this paper. We can go down and see more uh, thing. Actually, when you look at the way it does it, it's quite, let me show you some examples. There's a certain interpretability to it. And I think, as is quite the fashion these days, um, most of the real things come in the appendix uh, or come much later, yeah, after the appendix, after the references in the appendix. So look at this. I will leave aside the contrastive loss, etc. It's exactly sort of what you would expect it to be if you're familiar with this domain. Right. Look at this. I want you to pay attention to this. Figure 5 is in some document, example from the energy test set, which they created. The x-axis is hour, average hourly generation, how much power is generated, which is of different types, nuclear power, biopower, I don't know what that is, but geothermal, solar, wind, hydro, natural gas, other import and imported power. Suppose the question is caption, the image depicts. So here's the prompt. You're an assistant specializing in document analysis. Given a table or a figure, you have to provide a detailed summary of the content in maximum 3,000 characters. Your summary should be qualitative and not quantitative. Here is the table figure to analyze image. Answer only with the caption of the table. So here you're asking it for caption. It says the image depicts the hourly generation profile, illustrating the contribution of various energy sources over a 24 hours. The data is presented as a stacked bar with the x-axis representing the hours of the day from 1 to 2, and the y-axis shows blah. The bars are segmented into different colors, blah, blah, blah. The chart provides insights into the temporal variations in energy generation across. So, guys, do you realize that this is really very good? This machine is understanding what it is, what you're looking at. Caption. So, again, a captioning exercise from the government reports test. What is it? What exactly is it? Image shows a table titled System of Records. So, for example, it knows that this part is the title. And then it goes on into great detail. It's pretty remarkable that it can do that. Now, you look at this. This is French, so I can't make head and tail out of what it is, but apparently it's pretty impressive result because these white spots that you see are highlighted. What I can make out is this word Kazakhstan, and wherever the word Kazakhstan is here seems to be pretty much highlighted. But beyond that, I couldn't make head and tail out of this image. So, is it French? I would imagine it's French, right? Quelle party, whatever. So let's go back to the safe harbor of English. Query, what is the chemical formula for the ferroelectric material? Lead, zirconium, titanium, PZT. And look at this carefully. Similarity of the image patches with respect to the underlying tokens in the user query. This example is from the healthcare. So when you ask it this query, see where is it finding its max similarity. It is going and highlighting this area, which is this. Here is the formula.
Mm.
And it is going and highlighting the formula. It's also going on because we use the word formula here. It is also highlighting this and so on and so forth. So it just goes to show that Colbert is pretty good at picking up or at least giving attention to the areas of the picture that matter. Now, there are more metrics, additional metrics, and in many of these metrics, you again see that ColPali tends to be very good. And I won't go result after result. Uh, they have created, one of the things they did is they created a data set which is visually very rich. And I think this will become a new way of benchmarking how good your RAG system is or your querying system is, information retrieval system is a multimodal domain, because they have really taken a lot of pains to create a wonderful, wonderful benchmarking data set, right, across many domains. So they do it across many domains, many languages, just very good. And many modalities, of course, figures, text, charts. So many modalities, many domains, many languages. And what they show that through all of it, ColPali shines through, and it seems to be beating all the prior methods. So that, folks, was the reading of this particular paper. I hope I did manage to convey the main idea of the paper. I'll now open us up to question answer. Any questions, guys? Are we understanding it? By the way, just to whet your recollection, what did we do? I'll just give a very quick brief on what we did. We started out by, now you know why I started out with Colbert. Colbert gives you late interaction, very high quality results. Right? If you notice that the very expensive way of doing it is to pass a query in a document to, let's say, a BERT model. You will get very good accuracy, but you will get very, very, very high latency and compute cost. So the mean reciprocal rank is very good. But Colbert achieves practically the same performance in terms of model quality or inference as BERT does, but it achieves at orders of magnitude lower query latency and orders of magnitude lower compute cost. Right? And of course, it is just impressive how well it does. So that was the Colbert paper we did. Then we did the Pali paper, which basically said that, if you remember, we covered it last time, that you can take a contrastive visual encoder, think clip, except that you don't think clip, you think siglip, which is better. And then you pass in a text to train it. You pass it through a full language model. At that time, universal language model, when that Pali paper was written, was doing very well in Google. And so they used, I'm pretty sure it's a Google paper, isn't it? Yeah, Google paper. UL was doing very well. So they were passing it through a full transformer encoder decoder, like the classic attention is all you need architecture. And then they were getting the generation. But later on, what Polygemma did is it simplified things. And Polygemma, if you notice, its simplification was that it replaced the full model with just a tiny Gemma 2 billion parameter model, a decoder only model. The other thing it did is, even the SIGLIP, it optimized it down to 500 million parameter model. And they found that even if you do this, use tiny, tiny models by today's standards, nevertheless, you get state of the art performance. And therefore, in the progression of that journey, what today's paper says is, with those ideas put together, now you can bring it to the power of RAG. I mean, it's just a new way. Instead of doing the traditional RAG, you now have a new way to deal with visually rich documents in your pipeline, right? And that is the value of this paper. I don't know. To scroll down. Yeah. Questions, guys?
Phenomenal paper.
It's a very, very, very good
It's a,
paper.
it's a, it's like, I wish there is a, just like the playground, there is a ColPali playground.
Oh, it is there. Actually, ColPali is very, very easy to use. It is there now in Hugging Face, and downloading and using it is not at all hard. In fact, if you are taking the RAG course with me, the RAG course starts in, when does it start? Mid-October. Um, when you do the in-depth retrieval augmented generation course, we take you through all of this.
Nice.
It's very much a part of that.
But there isn't any, like a playground, there isn't a playground up there.
No, out of the box, I don't think there's a playground. But
There's
but using it actually isn't that long. And when you do that, we will of course give you such a playground here at Support
correct.
Vectors on our machines.
Asif, can we go back to that that Maxim slide or that page?
Yeah, this is it.
No, that had was visual. It had it was vectors coming from both sides with the projecting layers. The
Oh,
very
right,
first
right,
on the
right.
right side, yes.
This one,
Yeah.
Maxim.
Sorry, can we, I think the best one would be that question. It was the energy model. That's what the question was. Sorry. I rectified my question. Can you go back to that energy
Energy? I don't remember.
the this was in the examples in the end that they gave multiple examples.
Oh, yeah, yeah, yeah. That's right.
Hmm.
Where you could see the maxillarity is a score. It will be from 0 to some number,
Some
right?
number, right?
And so the higher the number, the more white it is. I know what you're talking about. Let's go back to that
So
example.
my question there is,
Yeah,
so if you zoom in, let's just zoom in here a little bit. Yes. So
hang on.
let's say if
Yeah,
I change the question, not this,
the next
that
one.
one.
That
No, the energy one. I think you were there earlier. Yes.
this one.
Yes. So imagine if the question I change it to saying, tell me on the 12th hour, what was the solar component? Just
That
saying,
is right. Yeah. So you can actually do that. And one of the exercises we'll do is literally that. But it is mentioned somewhere in the paper, but we do it more as an exercise out here.
oh,
Let
there it
me,
is. I think that question, but it's not, it's in a table actually. What is
right.
the
What
projected
type of
free?
accounts or products allow investors to defer payment? Yeah. So things like this. What is the projected peak electricity demand, right, for the year
Hmm.
2030? And the amazing thing is, it is able to answer these questions.
All these, there must be a quick, this must be already out there actually to read.
This is the Vidore data set. And basically, it's a benchmark, and you can see how good models do. Obviously, they have put this benchmark, and I'm sure ColPali does this very, very well and gets a very high score on this, answering this kind of questions.
If the financial guys must be using this to break open 10K reports and
See, yeah. See, 10K reports is a very good filing report because it's filled with tables and so on and so forth. Actually, I was asked this question last year. Somebody asked me that, hey, all these companies have 10K filings. I want to start a software company or a startup in which I take the 10K filing of all the companies from SEC and open it up to question answering by saying which companies have a revenue stream between this and that, which companies aims to spend more than 200 million on some generative AI next year, blah, blah, blah. And I know that one team tried to do it in those days. And when they started doing it, I took them through the whole process of table data extraction. All I remember is that they managed to get to quite a bit of success, but they were very, very tired at the end of the exercise.
oh,
Right? So this does represent a significant simplification.
phenomenal paper.
Wonderful.
Thank you.
Nice. Ah, you're welcome. Nice, Shiran. Nice you liked it. So, guys, any questions, anything else before I close today's session? I'll stop the form.